So 67 has the vector r equals 2 plus 7t times the unit vector I plus 3 minus 5t times the unit vector j. So it's going, and it asks me to write this in what? Slope-intercept form, right? Yeah, okay. So what I'm going to do is I'm going to start just by distributing this I through. And the j through. And then what I'm going to group together now are the parts with the t's and the parts without the t's. Like this. Is that okay so far, Maya?
Yeah.
Okay. So 2i plus 3j is just the unit vector, or is just the vector 2, 3. And the vector 7i minus 5j is just the vector 7, negative 5. And now it's in the same familiar form as 63 and 65. So my point can be 2, 3, and my slope can be negative 5/7. So I can say 3 equals negative 5 over 7 times 2 plus b. And if I add 10/7 to both sides, that gives me 31 over 7 for b. And that should be my final answer. Yes, good. Is that okay there, Maya?
Yeah.
So really the trick there was just doing a little bit of pre-processing in the beginning to get it into that vector equation form that we were more familiar with, by writing it as, you know, like I plus j and I plus j. Right, that's what we did there. Does that feel good to the rest of us on what the trick was to deal with that? Devin, you have follow-up on this or something different? Okay. 55 asks us to determine whether the following point lies on the line. Okay. So in 55, we're given the point 5, 2. And the vector line equation we're given is this. Okay. So 5, 2 is a point, but it could also represent a vector output to this vector line equation. So what I'm going to do is I'm really going to think about this as the vector 5, 2 equals negative 3 plus negative 2t. And then 14 plus 3t. You okay there? And what I'm going to do now is I'm just going to solve for t in each of these kind of rows. And if I get the same value for t, then yes, this would be a point on the line. If the values for t disagree, no, it wouldn't. So when I do the first one, I add 3 over, gives me 8, and then divide by negative 2, I get negative 4. Here, if I subtract 14 over, I get negative 12, and I divide by 3, I also get negative 4. So yes, that point is on that line. Does that feel good there? So again, that's all you need to check to see if that point is on the line. You just need to see if there is a value of t that's going to output that point. So all I did is I plugged the point in and solved for t in each of for the x component and the y component. And if I get the same value of t, then sure. In fact, here's the value of t. -4 will be the value of t that gives me that point. If they disagree, then no, you can't. Is that okay there? Okay. Bridget. 78. We're plotting there, huh? Okay. So let's see. We have 2, -1, 5. Oops. So I'll make myself an XY axis here. All right. So we want to plot that point. So the first thing we'll do is draw in some tick marks. So there's 2 tick marks on the positive x. There's 1 tick mark on the negative y. And there's 5 tick marks on the positive z. Everybody okay there? Again, remember x, y, and z. This way. Okay. So what I'll do is I'm going to draw a line that goes through 2, 0, or 2, 0, 0, and is parallel to the y-axis. I'm going to draw that. And then I'm going to draw a line that's parallel to, or that goes through the point 0, -1, 0, and is parallel to the x-axis. So that's that. So this becomes like the base of my prism that I'm going to make here. Is everybody okay there? And the intersection of those two is going to be lower left corner on the top of my box that I'm concerned with. That's where the actual point is going to lie. Does that feel so good so far? All right. So now I'm going to go up here and going to do the same thing here. And that's going to make the top of my box. And then I'm going to go like this much down and this much down to make my other 2. So the point that I actually care about is like that one there. Can we kind of see where the box comes into play there? It just helps me kind of orient that that point in space a little bit. So I'm able to get a little bit of perspective about where it's at. So when you're looking at this, you have to imagine it in 3 dimensions, which is tricky. I know, it takes some imagination. But once you kind of see it, it's like one of those magic eye pictures, and it should click in and be like, ah, okay, I see it floating there in 3 space. Sam?
Can you do any from 69 to 72?
Yeah. Which ones were you guys supposed to do? Okay, then I'll do an even for you. That's what you get for being that general for me. So here's 2 points. What I'm going to need out of this is I'm going to need a slope. Well, that's relatively easy to calculate. So I can turn that slope into the slope vector 5, 1. And then I need a point vector. So I could use either one of these 2 point vectors. It doesn't matter which one. I'll just use the first one.
I thought you said there could be multiple answers.
Yeah. And that we could write this slope as 10 over 2 or -5 or -1 over -5, or, you know, like there's lots of different ways to do that. So my vector equation is just the point vector plus the slope vector times the parameter t. And I'm done. So that's one example. There's lots of different ones you could pick. I'd be surprised to get anything significantly different than this one, other than maybe using the other point or whatever. But, I mean, there's lots of answers. In fact, infinitely many.
So I have just kind of a random question.
Go.
Should it be a plus or minus for this t?
Well, it doesn't. It should be we write a plus, really every time, because we're allowing but it doesn't really matter because t can be any real number. So like t can be negative. You can pick negative values for t. So like if it was minus, then the negative values of t would give you the positive, and the positives give you the negative. So it doesn't really matter.
Right.
But the equation and the standard is to write that with a plus sign there.
Right.
But it doesn't really matter. And the reason is the slope vector is really just kind of describing the direction. And if you're talking about a line, it doesn't matter if the direction is going this way or 180 in the other direction. It's still going to be a vector that lies on that line. So whether the slope vector is positive or negative doesn't matter. Is that?
Yeah, that makes sense.
So that's a good question, right? Because there's kind of possibly a lot going on there. No, hold on. It's not Meredith. It's Allison. Okay. Of course. It just took me a minute to get there. It was a long weekend. Is that good? Any, Carol?
Can you do 79?
79? Okay, so it's just another point to plot. Okay. All right, so again, I'm going to start by putting in my tick marks. So 1, 2, 3 on the negative end of the y-axis, or x-axis. And then 1, 2, 3, 4 on the positive end of the y-axis. And 1, 2 on the negative end of the z-axis. Okay? So I'm going to start by going to the last point that I put on the x-axis and just drawing a line that's parallel to the y-axis. And then I'm going to go to the end of the y-axis and draw a line that's parallel to the x. And what this has done is it's created for me, in this case, it'll be the top of my box. And it's this point that I'm really concerned with. So the bottom of my box, the back right corner of the box is the part that I'm going to be interested in. Is that okay there? Okay. So to complete my box, I got to go down here. And then I'm just going to draw the rest of this with some perspective. Maybe drew, oops a daisy. Well, I guess it doesn't really matter. It's all done now. But you're going to have something like that, where this is the point that we're concerned with. Does that feel okay? I guess I should draw that other. You can kind of see that. So drawing the box helps kind of see where it is in space. And I wish I wouldn't have deleted my axes there. I got a little eraser happy. But you got what you needed there? All right. We ready to go, Brockton? 57. Okay. So this is just like 55 was. The only difference is that we have our vector written in, this standard or linear combination form. Okay. So just like I did on 55 when we did this, or I'm sorry, not 55, 67 that Maya had asked about, we're going to rewrite this as a, back into standard IB form or whatever. So I'm going to have 1, 3, and then plus -4, 7, t. So plugging in my x's and y's, I just need to solve for these two equations then and see if I get the same value for t. And since I get different values for t there, I know that they're not on the same line. How's that, Brockton? That's good. Were you clear on how we did everything there? Yeah. Again, all you have to worry about is like, you got an I, and then you got a J, and you do that for each of for the point vector and then for the slope vector, right? That's basically all I'm doing. Okay. Last call on this. I think we've done a good assortment here, a little bit from everything there, right? Cool. And again, notice that none of these took tremendously long, right? They're all relatively little work to do in terms of actually solving the problem. You have to be comfortable with the notation, be able to move back and forth between these forms and understand what it is that you're trying to do, but the actual work itself that you write down, there's not too much of it, right? We've certainly done a lot of things that were much longer than those ones were. Okay. Next up, we're going to start talking about 3D vectors. So when we talk about the ways to represent a three-dimensional vector, we have our regular component form, where again, remember what this means. It means the origin is the initial point for our vector, and the terminal point for our vector is the point ABC in this case. The same is true for the IB component form. Just instead of writing it as a row vector, we write it as a column vector. And then there's a linear combination form. And our new unit vector for the z-axis is k, so we have I, j, and then k, just in alphabetical order. Everybody's okay with that? So if we give you 2 points and ask you to write the vector AB, and let's just write this first one in component form. We can do this the same way we did for 2-dimensional vectors. Do you remember how we did this for 2-dimensional vectors? We used the head minus tail rule. So which one of these is the terminal point for the vector, A or B? Which one is the terminal point for the vector? Point A or point B? B. How can you tell? That's correct. Yeah, the head of the arrow is over the B. Everybody's good with that? Okay. So we're going to do -5 minus 3, -6 minus 8, and then +1 minus a -4. Everybody okay there? Or if we want to write it as IB component form, how would I write this? I'd write as the column vector -8, -14, +5. Everybody's okay there? Or if I want to write as a linear combination, how would I write it? -8i minus 14j plus 5k, where I, j, and k are just our unit vectors. Everybody good there? Hopefully then it's easy to see how to move back and forth between these 3 different forms, right? Okay. What if I wanted also the magnitude of AB? In 2 dimensions, how did we do this? The square root of is correct, square root of the first component squared plus the second component squared, right? How do you suppose that changes for 3 dimensions? Yeah, you just have a third component in there, but it's all still under the same square root. Everybody happy with that? So that's like the square root of 269. How do you suppose we figure out the direction for this vector AB if we're in 3 dimensions? So now you're talking, instead of like having a unit circle, what is the 3-dimensional analog to a circle? A sphere. To describe a direction inside of a sphere, you actually need 2 angles. And we're not going to do that in this class. So we're not going to talk about the direction in 3 dimensions. So let's say we want to find a vector W that's equal to 2u plus v, where u is the vector -2, 4, 7, and v is the vector 7i minus 6j minus 9k. Do you remember how we do scalar multiplication with 2 dimensions? We just multiply the scalar to each component of our vector, right? So 2u is just going to be -4, 8, 14. Right? To add 2 vectors, they should probably be in the same form. So let's write vector v in component form. And then to add vectors in 2 dimensions, how did we add them? Yeah, we just added them component-wise. We add the x component, add the y component, and add the z component. We'll do there's no z component in 2 dimensions, but that's how we'll do it in 3 dimensions. So we get 3, 2, 5. Everybody okay there? Sound good? Okay. What if we wanted then to graph that vector W? Oh my goodness, come on, computer. So the first thing we're going to do is we're going to plot the point 3, 2, 5, and then we're going to draw our vector from the origin to that point 3, 2, 5. Just like we did in 2 dimensions, right? So 1, 2, 3 on the x-axis, 1, 2 on the y-axis, 1, 2, 3, 4, 5 on the z-axis. So we'll start by drawing our vectors here. Okay. So that creates like the base for my box. So I'll draw up and then over And then we can do that one up. Okay. And so the point that we're interested in is the one here. So my vector kind of looks like that. Yeah. So what I'm looking at is the intersection of those two lines that we drew in the very beginning. So since that's like the front right corner of my box, I'm just looking for, when I project it up into the third dimension, the same corner. Does that make sense? So it's just kind of a visual thing. Okay. Everybody's good with this. So far, so good? So everything that we just did is exactly the same as two-dimensional vectors. You just have a third component to work with, but it doesn't really change anything, right? Didn't make anything appreciably more difficult. Same thing that we've been doing. We just added a third component. So next up, okay. So for 2D, we said we had the vector equation R equals R naught plus VT, where R naught is our point vector, and V was our slope vector. Now, if I have three components, if each point has an x, y, and z coordinate, what the heck does slope mean? In 2 dimensions, we define slope as rise over run, correct? Change in y over change in x. If we have a third component, does slope really make sense to have that kind of a definition there? Not really, right? So rather than thinking about that vector v as a slope vector, we're going to think about it as a direction vector. Because that will serve the same purpose as the slope vector, right? Yes, Adam. Of course. Okay. So let's look at an example here of what we mean. So let's say we are given the points 5, -2, 6, and -3, 4, 1. And we want to write the vector equation of a line through these 2 points. And maybe we shouldn't say maybe I should say a possible, because just like for 2 dimensions, there's lots of possible answers, right? Sam, you asked about this during the homework check there. So what we're going to do is we're just going to pick one of these 2 vectors to be our point vector. Does it matter, or one of these 2 points to represent our point vector? Doesn't matter which one we pick. I'm just going to pick R naught. So if I call these points A and B, my direction vector then could either be the vector AB or it could be the vector BA. Doesn't really matter which one you use. And you know what? That's really easy to find, right? Let's say we find AB. So it's going to be -3 minus 5, 4 minus a -2, and then 1 minus 6. Oops. And so there's my answer. Everybody okay there? So the key takeaway here is that instead of using a slope vector in 3 dimensions, because slope doesn't really make sense inside of 3 dimensions, we just need a vector that passes through those 2 points. So just take the 2 points and put them into component form vector, and that's fine. That's all you need to do. Doesn't matter which way you go, whether you do A, B, or BA, it's still fine. So that's pretty easy, right? Still not too bad. So let's determine if this point lies on this line. Okay, so let's try to do this the same way that we did with 2 dimensions. So just like we did before, we're going to drop that point in for our R vector, and then rewrite the right-hand side of that vector equation as a single vector. And then we're going to solve each one of these equations for t. And since we have the same value for t in each of the 3 situations, obviously that point lies on the vector, or on the line, right? I think, just FYI, if you're looking at the book notes, I think I put a subscript on all of these t's when we wrote the notes, just so you're not confused about what you're really doing there. Do you have to do that? Definitely not. But just in case you're looking at the book and going, what the heck are these doing? They're just naming the t parameter for the x's, the t parameter for the y, the t parameter for the z. Okay with that idea? I want to stop here today.